All right, so maybe it'll work this time. All right, our lesson today is on what's called inductive reasoning. That's a certain kind of thinking that we're going to do. Inductive reasoning, we're going to look at some patterns and make what are called conjectures. We'll try and explain whether those conjectures are true or false, and counterexamples will help us do that. So a little bit of vocabulary up at the top of your notes to begin. But are you someone that observes patterns? You like patterns, number patterns, picture patterns, things like that? A lot of mathematics was developed by mathematicians who've been curious about something, trying various things. Maybe they wondered, oh, how far is it if you go around this circular thing compared to going straight across? And trying that in different situations is how they came up with the value of pi. So, are you a pattern person? Describe the pattern, find the next item in the pattern. January, March, May,
July, June,
June,
or July, one of those.
or July? How about if you describe the pattern?
July, it's every other month.
Okay, he said every other month, so it would be July. Okay. How about the pattern 7, 14, 21, 28?
21,
42, 49.
John, what's the pattern?
Going up by 7.
Okay, what do you mean going up by 7?
Counting by 7.
Every
Maybe adding 7, going up, okay. So multiples of 7 is the way that the PowerPoint described it. The next multiple would be 5. So the next number was 35. Okay, a little pattern with pictures. And you have to draw it this time. So you've got some paper there. Draw how the next triangle would look. When you draw the pattern, this one's not maybe too difficult to draw accurately, but drawing it, shade it if it's supposed to be shaded, turn the right way, color that needs to be there. There maybe is more involved in some of these patterns. Okay, which way's the triangle look the next time? Kind of pointing to the right. So they described it as rotating 90 degrees counterclockwise, opposite from what a clock does, so that makes the straight go up, turn it 90 degrees again, or 90 degrees again. So the describing the pattern, that's one kind of wording you can use as far as rotating it. Here's another number pattern. What would be the next one in the pattern? Start raising my hands. What would be the next one in the pattern? Not 0.0004. Need to have a 0 first. So 0.0004. Okay. The pattern did have that 0 in front of the decimal point. A little technicality. How about 1, 4, 9, 16, 25? Don't shout it out. Let people think. How would you describe it? I think they figured it out. Look at the pattern. Not too many yet. Or decide if it's going up or going down. And is it going up by usually increasing is usually either adding or multiplying most often. So is it adding something? Is it multiplying in some way to come up with the new numbers? I think it's clicking for some of you the more you look at those numbers.
It was and then it wasn't.
It was and then it wasn't? You had it and it disappeared?
It disappeared with nothing.
All right, how many think they've got the pattern figured out this time? Okay, we got a little bit more. And share with me, Shay.
Versus 5 and usually add more
what do you mean by first it was 5?
Well, I meant 3 to 4 was 2, I mean 3. And then you added 2, so it'd be like 4 to 9 would be 5. And then 9 to 16 would be 7.
I think she's talking about how much to add each time. You added 3, added 5, added 7, added 9. So what's the next amount to add? 11. How do you describe those numbers you're adding? They are the next odd numbers each time. Okay. Anyone look at that pattern differently?
Right.
Okay, look. Perfect squares. In other words, 1 squared, 2 squares, 3 squared, 4 squares. That's how I looked at it. But the adding the odd numbers works also on that one. And so
I don't know perfect squares,
So the point of that is there's more than one way you can describe a pattern sometimes. Okay, here's another one. Do some thinking.
Ooh, this is tricky.
Figure it out.
I know.
Got a couple? This is what's called, this one is called Fibonacci's sequence.
Whoa.
Famous mathematician established it, and it works for a lot of things that happen in nature, the way that this grows. Abby?
So I think it's like starting on the second one, it's just the pattern.
Okay, just a second.
Oh.
You guys are
Ooh,
distracted.
I got it.
Okay, Abby, I'm sorry.
Okay, starting on the second one, it's just like adding the numbers in the pattern.
Okay, adding the numbers that were in the pattern, so add 1 to get 1, add 1 and 1 to get 2, add,
No, starting on the second one.
is this the second one?
That one.
Okay, so starting on this one.
Yeah,
Okay, add what?
add 1
Add 1,
to get 2.
add 1 to get 3.
Add 2.
Add, why add 2 now?
Because it's the next one.
Okay, you understand what she's
Yeah,
trying to say?
Like you say 1, but there's nothing behind it, so you get 1 again, and then you add 1 and 1, so you get 2, then you add 2, and then the next 2 numbers behind it, then you add 3, and you get 3, then you get 3, and then add 2 and 1, then you get
Okay.
5.
He said something about the numbers behind it. Yes.
They did.
Okay, so I think you're trying to say, add the 2 previous numbers to get this one.
Yeah.
Add these 2 numbers to get the next one. Add 2 and 3 to get 5, add 3 and 5 to get 8. Yeah, the 1 and 1 were really the beginning of the pattern. If you said here, I guess you'd have to think of a 0 being in front of it, so maybe just starting at 1 space from what you were describing. So what comes next in the pattern?
13 plus
13 plus 8,
8. Big number.
21.
21.
21, and then what, 34 after that. So you're adding the 2 previous numbers to get the number you're on. Fibonacci was a mathematician, and he observed things in
Is he
nature.
Italian?
Is he Italian? Yes, definitely sounds like Italian.
I'm done.
He observed the rabbit population as they were born, and the number of offspring, and the number that had expired, I guess. And then if you look at flowers and rings of things that grow in nature, this is the number of like petals on each ring as you go around, as it gets bigger and bigger. So you'll see that number occurring a lot in nature. Okay, here's another picture pattern involving a little bit of different colors, if you can tell. You're gonna have to draw and describe what's the next item in the pattern. Trying to figure out what a good way to pair you up today would be with all our missing people.
We should pick
So,
up.
well, that takes a little bit long. Why don't you two pair together, you two pair together.
But I've already.
And that's about these two.
You're making it more.
Okay, discuss this one with your assigned partner.
Well, I have
Can
no
I do
idea
that?
what the pattern is. Or we're
Yeah, something like that. Yeah.
Did you get it?
Something like that.
Because 4 rows make that, but do you
Okay,
just count.
any decision on those blue lines in the middle?
Maybe it's more like.
Okay, need to do it. You don't really need them? Okay, the sides would tell you that you have a 6-sided figure that you need to draw, okay? But obviously, there are something
3,
with
4,
those
5,
blue
6.
connecting segments.
Oh, that's like how it's supposed to look if you connect the corners.
So, yeah, what do you need to connect? And I guess I'm drawing this with a flat bottom, just like the others had a horizontal bottom to it. So that is part of the pattern, it has to be sitting that way. Now in blue, what should I connect? All the points, so this corner to this corner?
No, corners.
Okay, so this one, this one, this one?
Yeah.
Okay, from here. 1, 2, 3 more.
So complicated.
That one's already there. So you're drawing in what will later be defined as diagonals. Those are all the diagonals. Diagonals don't necessarily cut it exactly in half, but you're connecting all corners that, the only ones you're not connecting is the ones that make the sides of the shape. All right, any group with that, right? Got it. Two people. Okay, so that's the next item in the pattern. So sometimes it's a little bit more complicated drawing it or describing it. I don't know if having another picture in that sequence, how many figures do you need? How many numbers, how many figures do you need before you can come up with the next one? What would be a minimum to establish a pattern? I think 3 would be a minimum. I think I would agree with you on that. On this one, perhaps if you had the 4th one, then would it be easier to draw the 5th one? Would you be able to see where to draw those extra blue lines if you had another one? Perhaps that would be. So as we're looking at patterns, can't even talk about a pattern unless you have at least 3 things to look at. All right, so what you are doing as you're doing this thinking is called inductive reasoning, and that was, I believe, the first definition there. Inductive reasoning is the process of reasoning that a rule or statement is true because specific cases or examples are true. You can use inductive reasoning to draw a conclusion from a pattern, and that's what we are doing more in right now. We're looking at patterns and seeing what conclusion we can draw based on it. Now the statement you believe to be true based on inductive reasoning is called a conjecture. So when you were telling me what comes next in the pattern, you were really making a conjecture. And probably if you put it in a whole sentence, you'd say, I think, or I believe the next thing in the pattern is 15 or whatever. That's your conjecture, it's what you believe to be true. It's not absolutely true, but we were trying to come up with a true conjecture. We need to talk about how you determine whether it's really true or false. So inductive reasoning is the thinking process that you're going through. Conjecture is what you come up with as your prediction. So here is a little bit more of a type that you would complete the conjecture. We need to find a pattern and complete this conjecture. The conjecture is the sum of 2 positive numbers is blank. Don't try and answer it right now or fill in the blank. What do we have to look at to develop a pattern? You told me at least 3 examples. So I need at least 3 examples of the sum of two positive numbers? Give me some examples. Nathan? 2 times 2? Not if we're doing sum. Sum doesn't mean times. Okay, 2 plus 2. Did I hear you wrong, or did you change?
Well, I just said that.
I got one.
Okay, 2 plus 2 is an example. 4.
21 plus 21.
21 plus 21. 22. What other kind of numbers can we have? It says positive. Couldn't we have 1.4 plus 0.6? 2 or 2.0? On your examples, you use the same number twice. That might give you a different answer than just what random ones are. But I need to stick with positives. 1/4. That's 1/2.
Six plus nine.
Okay. All right, let's not go interested. Okay, positive numbers. So notice I'm doing a variety. What kind of numbers do we have in our number system? What are the ones called that go 1, 2, 3, 4, 5, and so on? Don't think I've heard it at all yet. Natural numbers. Natural numbers. If it starts with 0, okay, 0, 1, 2, 3, 4, 5, that's whole numbers. Okay, what's another set? Rational, what were those? Okay, they can include fractions and decimals. As rational numbers were, as long as you can write it as a fraction of some sort, then it is, or I should say of some sort, a fraction where you have integer over integer, then it's a rational number. Real numbers, okay, real numbers do have negatives, they do have positives. There's a smaller set that involves negatives, integers. What's the difference between integers and real numbers? Real numbers have fractions, decimals, even things like pi or negative pi, those are in real numbers. We said rational numbers, there was also irrational numbers. Those were, give me an example of an irrational. Decimal keeps going but doesn't repeat, doesn't end. Pi. Okay, I, if you know what that is. Square root of 5. We can do square root of 4, that simplifies to just 2, but square root of 5 would be a decimal number that keeps going. So a lot of the square roots and pi are some examples of irrationals. Okay, that was just kind of a side idea because we need to think of those sets on a few of these problems. Okay, how would we fill in this sentence? The sum of two positive numbers is it even? Is it odd? Positive? Is it negative? I think positive. Got some other examples there. The sum of two positive numbers is positive. There's just a variety of the types of answers you would get. Okay, you work on this one. Create some examples, at least 3. Find the pattern and complete the conjecture. The product of two odd numbers is blank. Product of two odd numbers. Doesn't say they have to be positive. At least look at an example where it involves negative. Don't always use the same number times itself, because that might produce something that's not true if they're not the same numbers all the time. But don't use any evens. You need the product of two odd numbers. me one of your examples. Brandon.
7 times 3 is 21.
Okay, another example, Sam.
3 times 3 is
Okay, Jade. Someone have a different type? Can I? -1 minus 11 is -11. Any other type? Okay, complete the sentence, fill in the word for me, Riley. How did you fill in the conjecture there?
Are you still on the same
We're doing the product of two odd numbers.
Oh.
Okay, so how can we fill in the blank in order to describe those? Dalton? Okay, let's say what the answers were again. Those that gave me examples. Okay, we had -11. What was your answer? 21. What are some of the other just answers? 9, 35, 45. What kind of numbers are these that we're saying? Odds. Okay. The product of two odd numbers is odd. So you're trying to describe the type of answers we're getting all the time. Okay. There's another type. I want the calculation rule, so I want a little formula. In terms of n, so you're going to have a formula that has n in it. And it's going to tell me what the sum of the first n odd positive integers is. Now this is one that you probably should make a table to help organize what's going on. Okay, so let's make a table where we're going to have the first fact or first information as how many odd positive integers there are. There's one positive odd integer. There's 2, there's 3, there's 4, there's 5, and eventually we're going to say n is how many odd positive integers there are. We're supposed to come up with what the sum is. What's that mean? We're going to add them up. Okay. So what is the first odd positive integer? What's your just first odd positive number? 1. Is that an integer? Yes, integers are whole numbers and they're negatives. So we're talking about just the number 1. Well, if we add 1 to nothing else, our sum is 1. What are the first 2 odd positive integers? 1 and 3. We're going to add them together. And we'll get 4 for the sum. Add the first 3 odd positive integers. 1, 3, 5. Add those together. We get 9. Add the first 4. Add 1, 3, 5, 7. How much? 16?
So you're just averaging it by itself.
It looks like that. So this one was 1 plus 3 plus 5 plus 7 plus 9, which is 25. Okay, now in order to come up with like a formula, you probably will have trouble if you try and figure out how much to add each time. You need to think of it in a different way. Remember how Caleb described the pattern 1, 4, 9, 16, 25 earlier? Describe it again. Okay, perfect squares. So if I tell you this number is the sum, that number squared. Notice how that works on this pattern? If there are 2 of them, the sum was 4. If there's 3 of them, the sum is 9. So if I tell you how many there are, the total, when you add those numbers up, would be n squared. Now this type of a conjecture can help you predict things. So if there are 10, or the first 10 positive odd numbers will add up to be 100. What were the first 12 positive odd numbers? Integers, I should say. Add up to 44. what would the first 50 positive odd integers add up to be? That's 50. 25 with how many zeros? Two more zeros, so 2,500, 2,500. So you can use conjectures in that way to come up with a formula. So a conjecture is what? And what you think the pattern is. And why is he using think? It's because it's not proven to be true yet. But it's our prediction on what we're observing. All right, I want you to make a conjecture. Here's some information, how long whales are. We found some female whales and male whales. And we're going to try and make a conjecture about them. Discuss with your partner what kind of a conjecture. What do you see as a pattern in that data? Or how would you describe it? Turn to your partner and discuss what you're saying.
Females are usually larger than males. Should I not be offensive to the female gender?
Remember, it's recording. So. All right, how are you going to say this to try and make it true? Try it. Megan, what did your group come up with? Couldn't come up with anything. Why? They're just random numbers. Okay. Any group see any kind of pattern there? Now, sometimes real life isn't so straightforward. Okay. Were the female whales longer or shorter? Longer, except for the last one. Okay, so we cannot say that female whales are longer than male whales. Can't say it that way because we've got something that shows that that's not right. Can we change it? Did I hear some groups say generally or?
Females are usually
Usually, generally, more often. You gotta use some words like that. What if we would average? We added up the length of the female whales and divided by 6, and the same with the males. Will the average come out to be longer for the females? That was my thought. That's how I did mine. I said the average length of female whales is greater than the average length of male whales. So you can't just say female whales are longer than male whales. So conjectures in real life situation might be a little bit harder to come up with than just our number patterns and picture patterns. And what I had here was the idea of a counterexample. And as you were describing, saying that, well, we couldn't say that the females were longer because that last one doesn't work. That would be the counterexample if you had done your conjecture, saying that female whales were always longer. So a counterexample is a way that you can show a conjecture is false. Simply find one case or one example that demonstrates the conjecture is not true. That's a way to show it's false. A way to show a conjecture is true, we have to prove it. And today we're not ready to prove it. We're going to talk about that in the next few days. It's easier to disprove than it is to prove, especially if you're trying to do examples. Okay, on counterexamples, it could be a drawing. Maybe you're trying to show something. Maybe you're stating that in the top row, the last female whale was shorter than the male whales. Or it could be a number, like if you're trying to come up with a number that's divisible by 3 but not by 2, you can say 15 is my counterexample. So this is what you had just told me. So counterexample, don't think you have to rewrite the statement. All you're doing on a counterexample is giving an example, a situation, that demonstrates that conclusion or that statement is false. Are there some teachers that have you change a true statement to or a false statement to a true one on their tests? Okay, so I don't want you to do that. That's not what we're doing here. So don't get confused. All right, so here's an example to try. Show that the conjecture is false by finding a counterexample. So my conjecture is that for every integer called n cubed is always positive. For every integer. So when you're thinking of examples, searching for a counterexample, you have to use integers. When you cube your integer, I think, or the conjecture says it's positive. So a counterexample. Anyone think he has one? What integers have you tried so far in your mind? You're just sitting there, you're not participating. You need to try some integers. Pick an integer, whole numbers or negatives, okay? And then cube that number. Is your result positive? If it was, try another one. Another one. And then what number did you try?
I did 9.
9, but when he cubed it, that came out to a big positive number, 729. So that fit what it said. That's not a counterexample. 729 is positive. Sam? Okay, so he tried -3, and it came out with, when he cubed it, it was not positive, it was negative. So Sam came up with a counterexample, with his n being -3. Were there some others? -1 was a counterexample. -2 would be a counterexample. Any negative number in this one would be a counterexample. So how many counterexamples do we need? Just one. So we could say if n is, I think I might have picked 3, or -3. I tried +1, that didn't give a counterexample, but I tried the -3 like Sam did, and that came out to give me a number that's not positive, so my counterexample was if n is -3. How about this conjecture? 2 complementary angles are not congruent. Build on something we studied in geometry here. So think of 2 complementary angles. The conjecture says they are not congruent. Turn to your partner.
Oh, yeah.
Can be.
If you can come up with one example that shows that statement is incorrect, that's enough to show it's a counterexample. That's the one counterexample.
Whoa, we
All
got it.
right, Caleb and Nathan, what did you come up with for a counterexample? I need 2 angles. If your 2 angles are 45 and 45, they are complementary because they add up to be 90, but they show that that conjecture is incorrect because that says that they're not congruent, and you came up with one where they are congruent. That is the only counterexample to that statement. So you're not trying to make an example that fits what it says. A counterexample uses the complementary angles but shows the conclusion about them is not right. And you could not use supplementary angles. You could not use, what other word we've come up with, but you had to use complementary angles, but show that the statement was incorrect. Okay, here's a table of information. My conjecture, the monthly high temperature in Abilene is never below 90 degrees Fahrenheit for 2 months in a row. Can we use that data to prove that statement is false? Can we come up with a counterexample? Rylan?
from December to January, they're both below 90.
Okay, from December to the following January, those are both below 90.
February.
Tristan?
From December to February, those are all under 90.
December, January, and February, and I really just need to look at 2 months in a row. So either his December, January, or you could do January to February as the counterexample. I think that's the only combination. So there would be 2 counterexamples there that show that that statement was false. Questions, comments on that one? Okay, let's go back to a number one. Oops, looks like I didn't get my transition right. This wasn't supposed to be up here yet. Show that the conjecture is false by finding a counterexample. It said for any real number. So what kind of numbers should you be thinking of? Real numbers. Could be integers, could be decimals, could be fractions, could be positives, could be negatives. There are some numbers that are not real numbers, but you probably haven't used them yet. Okay, so pick a real number. It says when you square it, it's always greater than or equal to the number. Other than my example, what was I using? I used 1/2. Because when I square 1/2, I get 1/4. But 1/4, what I got when I square it, is supposed to be greater than 1/2 is what this statement said, and that's not true. So that was my counter example that demonstrates this is false. What would be some counter examples besides 1/2? Come up with something else that shows that conclusion is incorrect. 1/3. 1/3 when you square it is 1/9. 1/9 greater than or equal to 1/3. That is incorrect. So yes, that's a counterexample. Any fraction? Improper. Instead of improper. I'm going to say yes. I'd have to try a few more to see if any. How about any? Can it be like 5 1/2? Go with like 5.5 when you square it. Is that bigger than 5.5? Yeah, so we can't maybe say any. But if we limited it, I'm going to say that maybe any fraction between 0 and 1. So any decimal between 0 and 1 would work. Could I use a negative in any way? Negative number squared greater than or equal to the number. That's always going to be true. So there are counterexamples to that one. Did someone say 1? 1 would make them equal, so that wouldn't be a counterexample. I thought I heard somebody say 1. All right, let's go back to a geometry one. The conjecture says supplementary angles are adjacent. What supplementary angles are, what adjacent means. I might have to draw this one because adjacent has to do with how they're drawn, where they're positioned, if they're hooked together or not. And you create supplementary angles that are not adjacent. Discuss with your partner. Come up with anything?
Yes.
What's adjacent mean,
No,
guys?
it's not. No, there's only 2 angles.
So, in order for them not to be adjacent, you don't want them to share, you don't want them to be hooked together. So start with an angle. Give me a degree measurement. If you drew the picture right there where they're hooked together, that's not gonna work. Just draw one angle. Oh. Okay. Just add up to 100. So now draw a 145, it's not hooked onto that. Draw it, don't hook it on there, just draw it as a 2 Okay, could you do it? Okay, how does this picture need to be? You need to make sure the angles add up to 180, but don't hook them together. Draw them separate. So they're pretty close, but notice they're not hooked together. And mine added up to 180. So supplementary angles in picture form could be one example. All right, so inductive reasoning is the thinking process that you're going through. There's basically 3 steps in the thinking process. Look for a pattern. We looked at some number patterns, some picture patterns. We made a conjecture. Conjecture was what you believe to be true, but it's not proven to be true at that point. The 3rd step is either proving the conjecture or finding a counterexample. Proving the conjecture by examples would take forever, because to prove it's always true, you'd have to show all the examples. If you think about that, in a lot of situations, that's impossible to do. Counterexamples, one example that shows that using what it says you have to start with, like supplementary angles, the conclusion part about them is incorrect. So if it says supplementary angles, you can't use complements, you gotta use what it says. All right, do we need to practice anymore? We got 6 problems here. That'll only take us about 5 minutes. With your partner, answer these like on either your paper or marker board. And then we'll have about 15 minutes there to work on.
1 is 0, 0, 0, 7. And then that one would be an up arrow. I don't know about dividing, so let's see. Portions. 3 prime number. What's a prime number? That was just a multiplying by itself.
You get 1.
So 3 squared is 9. 5 squared is 10, so that's not true.
No, that's always.
Yeah, so that would be inaccurate.
Fair enough? Prime numbers?
I asked her.
Prime numbers have 2 factors, 1 and itself. So a number like 2 is prime, because you can only divide it by 1 and 2. 3 is prime, because you can only divide it by 1 and 3. 4 is not prime, because you can divide it by 1, 4, 2, and 3. So if it has only 2 factors, 1 in itself, that's prime.
Yeah,
So that's because you want to like
2 is a prime number and it's not odd. It's odd.
Because that would be your counterexample.
Are those the only prime numbers?
Or what?
Are those the only prime numbers?
Well, there's lots of prime numbers.
Like 37.
7's prime.
The most odd number.
I wouldn't say that, but the only even number that's prime is 2. Because if you get any larger even number, you can divide it by 2 all the time.
Yeah.
So most prime numbers are odd, but I'd say not most odd numbers are prime.
I think we're done.
Yeah.
About 30 more seconds and then we'll check.
Hey, I'm using that.
It's my pen.
I don't care. You drop all your pens. Look at
We're
that.
62.
My pen now.
Okay, first one. First one should have been 0.0007. Okay, second one, a lot of your arrows looked good. There were a few arrows that were not the square block kind of arrows like that. Okay, so just a normal like line arrow, no, you need the kind of block arrow that they were drawing. Okay, 3, true or false? True? Number 4? False. Counterexample? 2, and that's the only counterexample. Number 5? True or false? False. Counterexample? Okay, if you had a 90-degree angle and a 90-degree angle, that would be the counterexample. And number 6?
True.
That's true. Any odd number when you square it will be odd. All right, so there's one more check of understanding. The assignment is on page 77. The odds on the beginning. And for tomorrow, I'd like you to come with your notes for section 2.2 and 2.4 completed. That way we can focus a little bit more on discussing it rather than writing it down. That's what your assignment is for tomorrow. Get on it now.